pattern on here. Number of ways to guess any of these correctly here. We'll leave the general number of ways to guess X correctly here. Number of ways to guess all 6 of them correct. I know it's probably pretty straightforward, but maybe it's more useful to use this idea for ones that aren't so obvious when there's a whole bunch of different ways. How many different pathways lead to all 6 correct if we made a big, huge tree diagram? Well, there's only going to be one, right? But if we wanted to match everything else here, from the 6 roles, you want to choose all 6 to be correct. And you need 1 out of 6 to the 6th power. And you need 5 out of 6 to the 0 power. You don't have to include that really, right? Really, for this one, this is all it is. It's 1/6 to the 6th. For the rest of them, guessing 5 correct out of 6. 6 rolls, how many ways can you get 5 correct? That's actually going to be 6, right? You need 1/6 to the 5th power, and you need 5/6 to the 1st power. 4 correct, 6C4, 1/6 to the 4, 5/6 squared. And if you continue down there, right? 6C3, we're okay with this? We get all the way down to the bottom here? 6C2, 1/6 to the 2, 5/6 to the 4. And then this last one here, 6C0, 1/6 to the 0, 5/6 to the 6. Again, for this last one, really all you need is this, because this is going to be 1. There's only one way you can get them all wrong in a row. And there's none right, so you don't need that either. But just for the sake of completeness, that's all in here, right? Really, that's for that one is all you need. But for any of the other ones, that's the logic, right? So if you want to write this up here, getting X correct, out of the 6 rolls, you want to choose X, correct guesses or whatever. You want to have 1/6 to the power of X. And then this is the part that maybe you have to think about a little bit here. 5/6 to the power of 6 minus X. All right? So we're going to try and write the general formula here, and then you can use this concept. As soon as you start writing things like this, it makes it look harder than it actually is. It's not as hard as it may look from that. It's related to the binomial theorem that you learned before. There's all these terms here, right? When you do an expansion of this, P and Q, if you think of P as the probability of success, 1/6, and Q as the probability of failure, 5/6, that to the power of 6, each of the terms gives you part of that, right? This is like 1 to the 6. It's 1. That's all the possibilities. Each of these is an individual probability here. This is the probability of getting them all correct. 6C6, P to the 6, Q to the 0. This is the probability of getting 5 out of the 6 of them, right? And so on all the way across here. There's 7 different cases, right? There's 6 rolls, 7 different cases because you got 0 at the end there. We're going to use that to calculate some probabilities. I can't remember where I put the formula on here. We could probably skip ahead and write the formula right at the end here, or look at the formula anyways. And then you can go back and do some of those questions. This is the binomial probability formula. It looks like what we just developed there, right? The probability of getting X successes. Probability of, well, it says it up above there. I don't need to rewrite it. Probability of getting X successes here. That's what that means. P of X, probability of getting X successes. And you could call this Q or N minus X failures, right? Not Q. Sorry, we're using Q for the probability of failure, not that. If you're getting like what we just had there, 6 successes, 0 failures. Or 4 successes, 2 failures. Don't put a Q up there. It's 3 parts. Right? There's 3 parts to this. Number of different ways I would put underneath there. Number of ways to get that many successes. To get X successes. Okay? And this part in the middle here is the probability for all the successes. That part. Probability for the successes. And then the last part is probability for the failures, right? This part of it here. Probably for this, a specific example there is going to be more useful, right? What you wrote out before, some of those things. You can think of it as 2 parts if you'd rather think of it as 2 parts. You can just think of it as NCX is the number of ways, okay, just like up above there. That's the number of ways. And then you're multiplying it by the probability for one of the specific ways. P to the X, Q to the N minus X. That stuff together, okay, that part of this together is, okay, this part of it here, that's the probability for one of the ways. Number of ways times probability for one way. Okay, one of the ways. You can use that idea in here. You can actually write out the formula and use the formula if that's the way you want to approach it. Or you can just use the idea and just write it directly, right? Now this only works if the right conditions are met here. It has to be that the probability on each individual trial is independent. When you're talking about rolling a die and guessing the right number, if it changed from time to time, like if it's drawing cards out of a deck, if you said, if we tried to say, what's the chance on, if I choose cards from a deck and I don't put them back in, what's the chance that I'm going to get a heart, then a heart, then a heart, then a heart on 4 rolls? If I do put the card back, what's the chance of getting a heart each time I take a card? If I do replace the card on each draw. You can think of it as out of 52, I got a 13 to 52 chance, or a quarter, right? If I put it back each time, then it's a quarter, it's a quarter, it's a quarter, and it's a quarter. I could use this idea here, since the probability from one draw to the next is exactly the same. If I didn't put the card back, what happens to the probabilities as I go here? I got 13 out of 52 on the first draw. If I don't put the card back, well, it depends if I get a heart first or not, right? If I get a heart first, then it's 12 out of 51. If I don't get a heart first, then it's 13 out of 51. If the events are dependent, you can't use this idea because the probability changes, right? If you're not putting the card back, this is who knows what here. It has to be that these are independent and identical. They have to be identical, they have to be independent. The probability has to be the same. Whatever you're using as this P here, if it's 13 out of 52, it's got to be that every single time. Question? If you were doing this, you'd have to, well, I guess you could think through and see if you're rearranging the fractions, does it change, or for this, I mean, for cards or something like that, if they are dependent, yeah, you gotta think about each case, right? This, I would say, let's limit this to when these are independent, when the events are independent. When you're doing the same experiment over and over again, right? When you're doing the same experiment with the same probability each time. All right? There's lots of questions in here to try, both before and after this. We can look at using a graphing calculator in a few minutes here. I'm going to show you a graphing calculator function after. Can you go back and do some of these questions? Whether you're using the formula or not, if you're the kind of person that maybe wants to use the formula, you can write down, what do I know what n is, do I know what x is, do I know what p is, and do I know what q is? Write out the different things and then use that formula. Or you can just try and construct it just by intuitively understanding the formula, and you don't need to write it out. Figure out which one works for you and approach it that way. Okay, try doing those, check with somebody else.